Okay, so as I said, this is going to talk a lot of application. It's going to be a lot of physics talk as well as section chapter 3, I should say. So let's start with the chapter 3 stuff, the first and second derivative test. So there are a couple of key words or phrases you can look for to tell when you're going to be using a specific type of function. So remember, we had three big things we talked about in this class. Limits, which were the minor subset. Derivatives, where we could do more than one derivative. And then hit integration. So when you look at a fresh face problem, there's some key words or attributes that can tell you which direction you're supposed to be going in. And that's one of the most difficult things to figure out sometimes in a problem is, was I supposed to take a derivative or supposed to integrate? Because if you can figure that part out, you guys have shown throughout this year that you guys have the skill. You know, on a given day, you can do the work. The trick is, did you choose the right one? Did you choose it correctly? And did you then apply it correctly? So let's first talk about some basic things from physics that will pop up on this test. We'll talk about the first and second derivative test, and talk about some terminology as we go through it. So, key terminologies. Things like minimum, maximum, optimize. So, minimums, maximums, and optimizations. If any of these words or phrases is used in a problem, it is indicating you're supposed to look at the derivative. It does not mean take a derivative. There's a key distinction there. It means look at the derivative. In some problems, as we've seen on our tests, occasionally they will just give you the derivative and want you to just use it. So don't confuse I have to take a derivative with I need the derivative. Because if you're already given the derivative, you don't want to do it again. Okay? What you want to look for, if you see the words min, max, or optimization, that means your focus should be on f prime. Whether you're given f prime or you just happen to have f prime available because you can solve for it, like you want the derivative. So if you see the phrase minimum, maximum, optimization, or any variation on these words that you might see in an English class, if it says what's the highest it could be, that's the maximum, so it means to take and focus on the derivative. If it says what's the lowest it could be, it means that's a minimum, you want to look for a first derivative. These kinds of words and phrases pop up a lot, and they can throw you through if you're not expecting it, because it's not going to come out and say, hey, dummy, take a derivative. It's going to say, find the lowest value of this set. You're going to be like, oh, lowest means we're looking for the derivative's value where it is equal to 0. So, in general, the way we talk about these problems, how? What you want to do is you want to let f prime of x equals 0. These will determine where we actually could have possible, what we call critical values. Places where we could have a highest, places where we could have a lowest, places where it could be a minimum, places where it could be a maximum, or it could just be something else. What we look for is when f prime of x is 0, which is what we refer to as critical values. We then want to actually do something with them. We either want to evaluate them, that is an option A, is take those values that we find and just plug them in. That would tell you quite easily which one's the minimum and maximum by what the value itself is. But then you have to actually plug it into the original function. So you want to plug it into the f function. If you don't have the f function, this is not available to you. The alternative way is to use the first and second derivative tests to see how this function interacts around the values around it. As a reminder, the first and second derivative test require the ability to take a derivative. I know that seems like a weird thing to say, but like, it's a great one to use, but if you find yourself struggling to find the derivative of a function, or if it's a weird function that you don't remember the formula for, then this is not a great way to go about it. You want to see if you can evaluate instead. So, the first and second derivative test.
We need the power lifters to the office, please. We need the power lifters to the office.
Go on, Abby, please. I can see you. Okay. If the problem mentions minimums, maximums, highest, lowest, we have to focus upon the first derivative, f prime, and either evaluate the critical values when the first derivative is equal to 0, or look at the first and second derivative tests. So that's where we actually evaluate the values around those. As a reminder, how we did this was we found like a critical value on a number line. And what you did is you tested numbers in between and around these ones. So we tested, a number over here, a number over here, and a number over there. Because what we were determining was if the actual derivative does what it's supposed to do. If the problem mentions things like increasing, decreasing, this is also an indication of the first derivative, but this is a more specific application of the first derivative test. So you have to be able to take a first derivative or use the first derivative, find critical values, and take those critical values and test numbers that are around those critical values. So if you're wondering something to look up between now and the AP exam, you might want to refresh yourself on the first derivative test and how to use it. It is a common one that pops up on a lot of different examples. That same test is used, again, with minimums and maximums. It's also used with increasing and decreasing. Same basic form. Remember, positive values indicate increasing values, negative values indicate decreasing values, because f prime is the slope. The positive number indicates it's going up, negative number indicates it's going down. Next. Physics. So, there are two big parts of the physics. The first one is one we've already seen already. The second one is an application that we touched on, but we'll touch on more this week. So the first application is, given a physics-specific problem, how to work it out, how to find the actual values itself. So in this case, there's a reminder of this infographic. So you have three functions that exist. I can spell.
Man, I wish I could spell.
No, I can't spell. You have three primary functions that work for physics: position, velocity, and acceleration. Depending on which one you are given in the problem, you can find the others by using one or both of the techniques we've discussed. We can integrate the function, we can take a derivative of the function. It depends on what we want. Okay? So, example. If you are given the position function and want to find the velocity function, all you have to do is take a first derivative. So take a derivative with respect to x, or more commonly with physics, take a derivative with respect to time. That will determine what the velocity is doing and how that velocity is interacting. If you're given the velocity and you want to find the acceleration, it's the same process. If you're given the position and want to find acceleration, you just have to do it twice. Take two derivatives, a derivative first time, a derivative second time. If you want to work backwards and find the other functions, there are a couple ways to do this. The most common way is you can find the indefinite form just by straight integrating with respect to time. And again, it works for both of them. If you want to find a specific amount traveled, well, that just means integrate with boundaries. If you want to find an average speed, it means integrate with boundaries. If you want to find an average acceleration, it means integrate with boundaries. Determining these specific values means to integrate with certain a's and b's, what we call a definite integral. So, these kinds of functions, the big thing to remember about them is how they kind of all fit together. If you understand that they're just separated by an integral or a derivative, then if you know one of them, you can always work around to find the others. In physics problem, the common issue is that they will use physics terminology, and you'll have to remember how that fits in with mathematical terminology. As a reminder, some basic things that fit in with physics. It might say, what is the maximum speed? Well, if you're given the position function, that means take a derivative, define the velocity function, set it equals 0 to determine what the critical values are, and then take those values and test to see which is the maximum. If it asks for when is this car going to be traveling the slowest, that's a minimum position, it's a minimum velocity. And so, again, it depends on what you're given. If you're given the acceleration formula, you can still answer that question. Because it would just be finding a minimum, but you have to integrate first. Because you want to find the velocity equation. So again, depending on which equation you're given, you have options for what you can and cannot do. If you're given position, you can find velocity, you just gotta take a derivative. You can find acceleration, you gotta take another derivative. If you're given velocity, if you want to find position, you have to integrate. If you want to find acceleration, you have to take a derivative. Knowing how they all fit together in our two main subtypes is super important. Because otherwise, it becomes a massive, massive amount of problems. Like I said, the common issue with a lot of the physics will be that we use physics terminology in the problem, and we have to remember how those link to mathematical terminologies. All we're doing tomorrow is when we give out 10 problems, we're going to work on them together. And as we do, we're going to discuss them as a class to see how they kind of all fit. Keywords and phrases to look for. We're going to treat it like as if we were taking the AP exam in class, but taking it together. We'll talk about testing strategies, the thing that they taught you like in 6th grade or whatever. Ooh, I like certain words. Yay! The problem is in a lot of AP tests, like the AP Calc tests, you end up highlighting the whole thing. Because there's just a lot of stuff. And other problems, we only had a couple things, we just don't know what to do with them. So, this week will be a lot of working through examples on these kinds of applications. So we see examples that work specifically with the first and second derivative, and I see examples that work specifically with physics. And now that we have area and volume problems, those are also available to us. And the problem says find the area of this particular function, the volume of this particular function. That means we're dealing with a definite interval. Let's look at two examples today. Specifically, the first category, the first and second derivative tests. These are the ones that this application's got. Here we go. Okay. This comes from section 5.4, so that was the previous chapter. Horizontal motion problems. There is, if you ask me, Douglas, can you guarantee one question will be on the exam? You're taking the exam. Every year there is one horizontal motion question. Never fails. Sometimes two. There has never not been a year that there's a horizontal motion question. Now the trick of it is, the horizontal motion question is its own subcategory. We'll have at least 3 of them tomorrow to work through. And the thing is, it's exactly what it sounds like, and that's kind of what's weird about it. It is describing motion in one dimension, going back and forth. Picture a car on pavement. Okay, from the side, you're just looking at going back and forth, back and forth. Alternatively, if you take it into this class, think of like a spring. A spring pulls on an object either to the left or to the right, depending on whether it's under compression or tension. And as it pulls, it just moves that object in one dimension, forwards and backwards. So, let's look at an AP style question. Now, this should be considered a difficult AP style question. Well, let's look at it. Let's see what you guys think. Here's the following. It says, this is problem 141 in the textbook on section 5.4. It says, the position function of a particle. Now, the reason these are so common is because they're a specific application of physics. You can do this with particles. The larger the object, of course, there are more things like coefficients of friction that get in the way that make it less and less realistic. So they do it with particles because, well, they're very easy to say. There's no friction. Moving along the axis. Is the following function, x of t. So this is a position with respect to time. And that's kind of how you have to understand the equation. Remember, it's talking about the position function, so that means that whatever this represents position. So this is position, but it's respecting to the value of time. And they give us this weird equation. Capital A, e to the kt, minus b, e to the kt. Where a, b, and k are constant. The AP exam is fond of putting questions like this in the calculator portion. Why? Because they're jerks. Calculator can help us. Now, calculator can actually help a lot if you know how to use it correctly, but it will never give you the actual solution. It will only give you hints at what the solution is. So what the question says is, at what times t is the particle closest to the origin? So the first part is, at what times t, when, so at t is closest to the origin. Now, if they just came out and told you what to do, this would be a fairly straightforward problem. Now, the pieces are not easy pieces, but it would be a straightforward problem. We all know what to do if we all knew what piece it was asking for. But it phrased it this way. At what time t is this closest to the origin? So I have to figure out, what does that mean? Does it want me to just look at the actual equation? Does it want me to look at the derivative equation? Does it want me to look at the integrated equation? What does it mean for me to do? That becomes the issue. So let's ask a question. So you have all the pieces. We just have to figure out how the physics leads to the math. The position function of a particle moving on the x-axis is as follows. Boom. When is t such that this equation is closest to the origin? What is this question asking me to do? So we can look at the graph, look at the derivative. Of what? Those are good suggestions. I'm not saying either of them is right or wrong. But there's a lot of ways you can look at this. We have to kind of figure it out. So what are your thoughts? All right. Let me teach you how to read a question in physics. If you take a physics class, the sad thing is a lot of high school physics classes, and this is why I'm not a fan of high school physics, a lot of high school physics classes teach applications of the formula. Like, plug into this formula and you'll get the answer. Plug into that formula and get the answer. That's great. But that to me feels a lot like Algebra 1 Algebra 2. Mm-hmm. And to me, I get really frustrated when I come to my class because you know all the terms, but then when I give you a question like this, it's like, I don't even know what to look at. I don't even know what this is asking me. So let's remind you of key facts. Okay? First key fact. This function is the position function. So this thing is a position function. So if I plug in t equals 0, let's ask ourselves, what does that mean? It is the position at the starting time. Right? Make sense? If I plug in t is 0, that would be the position at time 0. What if I plug in t is 2? Position at time 2. What if I plug in t is 5? It's the position at time 5. This will always tell me the position. So then comes the next question. What does it mean to say that it is closest to the origin? And what? And what distance do I plug in? You have the exact pieces, but now you got to know how to use them. So this represents the position on the x-axis. So where does that mean we are closest to the origin? Where on the x-axis would we be closest to the origin? 0. So what this question is asking me to do, what the context that we have to understand is it's saying, okay, we want closest to the origin. Closest to the origin is when the x value equals 0. But we don't have an x in the problem, we have a t, except on the left-hand side. So what this equation is asking us to do is set 0 equal to a e to the kt minus b e to the negative kt. Well, actually, has to take integrate or take rid of it all. We're just asked when it's closest to the origin. Which seems weird, right? Because I just said that closest usually implies the first derivative. But keep in mind, this function is the position function. So if I want to find when it's the closest, I need to find the minimum value of the position function. This is it. Alternatively, I could look at x prime. Maybe x prime is easier to deal with, or it gives me slight variations on the solution. Remember, if I want to find the minimum position, the derivative is one of the best ways to go about it. So I now have two ways I can approach this problem. I could look and try to find when the x value is equal to 0, because that's when it should be closest. Or I could look at x prime. So let's ask ourselves what the second piece means. The first piece I think is pretty obvious. It's when will the position be equal to 0? But what if the position is never equal to 0? What if it never gets to the x-axis? What if it, here's the origin. I look at the graph of this thing. It starts over here and goes that way. Then the top version doesn't work at all. You see how you have to kind of read into these kinds of problems? They have a lot of big core concepts in them. So, what I want to do, if it ever equals 0, then this is like a shortcut. But the better way to approach this problem, every single time, is with a derivative. It will guarantee the right solutions. Because it'll tell you when is it the closest, when is it the farthest. Guaranteed. Okay? It will tell you the minimum and maximum values. In theory, that should also work. So, let's take a look at it. We're going to apply both. We're going to let this thing equal 0 and solve it one way. We're going to take 0 and solve it a different way. They will give different answers. One will give when the position equals 0 if it ever equals 0. The other will tell us what is the minimum value or the maximum value. Now, what's the problems with the derivative?
It's going to equal 0.
Actually, there's no particles because they're constants, right? Say again, Evan?
It's going to equal 0 because the particle is moving along a straight line on the x-axis.
So there should be a place where you So,
No.
it's almost like I needed to like. Particle. Very heavy particle. I'm sure there's like some physics jokes we made in here. Particle moves along a straight line. Right? In that case, we're assuming that that particle started in one place, at a velocity, moves in a direction, and either slows down or speeds up depending on what has happened. Here's the thing about this particle. This particle could start here, move to the left, slow down, slingshot back, go past the origin, slow down, and just do one of these over and over and over again. In which case, some weird things are happening physics-wise. Okay? Let's think about what each of those things is doing. The first method we talked about, setting equal to 0, will tell you every time it crosses the origin. Boom, 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 every time. The second method will only tell you the minimums and maximums, which is an issue. If I start here, that's 0, great, but I go sort of here, go sort of there. If I slingshot to the left and hit a maximum value, it'll tell me all the way over here is a maximum. If I slingshot back, it'll tell me all the way over here is a minimum. If I didn't stop somewhere in the middle, it would never tell me where it equals 0. You see the issue with these kinds of problems. The key understanding is how this little object is supposed to move and how we're supposed to approach it. So, I give you 2 things. We could look at when this position is equal to 0. This, by definition, should be when it's closest. But it will not guarantee it's going to work. Because again, it could slingshot, or it could never get to 0. It can only get close to 0. If that first technique does not work, then look at the derivative. Because the first technique will tell you when it's equal to 0. If that is never equal to 0, then we have to go to plan B. Plan B is, well, everything else. Again, this is understanding the physics of the problem itself, and it is not easy. But it's all the same pieces we've been working with all year. So, here's what I want you to do. Michael, Abby, Ricky, and Alexis. I'd like you guys to work the small teams today, talk to each other a little bit, verify your results. I want you to focus on this topic. Set this function equal to 0 and tell me, is there ever a time this thing should have a solution where it is closest to the origin? Okay, Sydney, Casey, JJ, I want you to work on the derivative. Tell me what the derivative is, and then we'll work together to determine if it has any solutions too. Okay? So in theory, 1 should guarantee solutions if they exist. Your guidance. If you guys cannot find solutions, then our version should solve for when it's a minimum and maximum, which can tell me the other parts, when it's close or far away. Now, you mentioned earlier, we're looking at the graph of this function. We cannot look at the graph of this function because A is unknown, B is unknown, K is unknown. But what you could do is pick some numbers for A, B, and K. Make A2, B3, K4, or something. They'll at least give you an idea of how the thing is acting in real space. So you can see, oh, this particle starts, it moves to the right because it's positive, and then it starts going to the left, so that means it's going to be going negative. You can see how they all fit together. But let's look at the graph afterwards. Okay? So you guys, set it when it equals 0 and see what happens. You free? Let's take the derivative. I'm going to start. Michael, I think you probably already have it. Do you have it when it equals 0? Nope. Take a derivative. You guys derivative. You guys. Let's solve that top piece. When will A e to the kt minus B e to the negative kt equal 0? And if you don't know, tell me where you're at. Okay, good. That is the first base, right? Okay, you 3 all work on that derivative. Okay, you're right. What were your next?
Like a random crap to see if it works.
Nope.
Yeah.
Terrible. I gotta solve for t, right? How do I solve for t?
Natural log.
Be natural log both sides. Yeah.
Oh, the constants. Oh wait, do the constant equal? Oh god. I forgot my natural log for a second.
Okay, so before I simplify this, maybe it'd be best to simplify the inside.
There's no numbers at all.
Right? This would become, so I have a product inside of a natural log. Good. This becomes natural log of A plus natural log e to the kt equals natural log of B plus natural log e to the negative kt. The e's should cancel out. Yes. So that goes away. That goes away. And what's left behind? We have ln of A plus kt equals ln of B. The negative would multiply to that positive and become negative kt. So far we're looking really good. Perfect. Add KT. Subtract ln of A. Okay, we end up with KT plus KT would be 2KT. And then ln of B is just ln of B minus ln of A. Good look at that. Divided by 2K. So this is one variation on the solution. There are other variations if you were to re-simplify these natural logs on the right-hand side. Example, remember, subtraction of natural logs becomes division. And we could also use that division to turn it into a number out front, which could then become a power. Like there's all kinds of ways to write this answer. This is one way. So that is good. Like this is a place where this is going to have a value of 0. Assuming this exists. Right? I should make that very clear. It's possible this doesn't exist at all. Because if ln of b, like if a b is negative, well then this wouldn't have an answer. Now I did say in the problem I believe that it should be positive constants. But there we have it. That's one solution. Okay? Alright, so we believe we have found a version that solves it with x equals 0. So in theory, this should be the place where it crosses the x-axis, and therefore would be closest to the origin. So our little marble, a little ball of fun, in theory, at this specific time, right there, should be dead center on the origin. As long as this value exists, that should be it. Now, what else could be asked? Well, if this value doesn't exist, we've got to find when it's closest. That's the first derivative. So what's x prime?
Any times, this is what we're guessing. You could figure out, say, A parentheses KT, and then in the parentheses E to the KT power.
No. There you go. Ricky's gone for 4 days and he's already at the top of the class. What the hell?
So you don't multiply by the
You multiply by the derivative, right? It's chain rule.
Yeah.
So the a is a constant. It stays up front. The e stays e, so it stays e to the kt. We then multiply it by the derivative. The top piece derivative of kt would be k, because k is a constant. So the derivative of 3t would be 3.
That's what we had, yeah.
Yep. Okay.
We had it there.
You were close. All right. So the question now becomes, okay, if that top number doesn't exist, what happens here? Well, we could find when it's the lowest and the highest. Now, for this problem, since I don't have an A, B, or K, I would assume we're supposed to do it the first way. For future reference, since this problem did not tell me A, B, and K, I would assume we're supposed to be doing it the first way. Because it wants to know when it's closest, that's when the position should be 0, so that should tell me what it is. If we had values for A, B, and K, and it turned out that we did the first method and it doesn't exist, there's never a time at 0, that's when we have to fall back on the second option. So keep in mind, the first option that us 4 did, that's the main way to approach this problem. The best way, because it said find the position, we have the position function, all we have to do is use it. If the problem said, hey, find the position, and we tried it and it didn't work, now we have a secondary option, the derivative. We've now got the derivative. So we're trying to find now critical values, determine the least and greatest value, or the minimum and maximum value. To do so, I will take this equation, set equals 0, and solve. So, I got it equal to 0. What do we do now? What do I do? What do I do? So I could basically follow the same basis as we done the previous one. Move the b and the kt over, and then do the natural log of both sides and see what happens. Yes. So some tricks here. There's a k in both pieces. We can cancel it. Remember, because k is supposed to be a positive constant, so that means it's like a 3, a 4, a 5, a 6, a 7. So determine where it is. Very similar to it, right? So this one probably has a minimum value where the ball is actually a little to the left of the origin. If I had to take a guess. And so every time this pops up with, it's probably over here at a minimum value, a minimum distance. And then slingshots over to the right. Okay, because remember, this is not a distance function, this is a position function. Okay? So when the position is 0, that's when it's on the origin. But yeah, these should be really similar. Now, at this point in time, if this is a graphing calculator problem, I'd pull out a graph. Now again, I cannot plug in the original equation. There's no way to plug this in. I've never seen a calculator that can do variables like this. There's ones that can do slider variables, where you can adjust it over time and stuff, but never one where it's just a blanket variable. Okay? So what I'm going to do is I'm going to write a new variance equation with 3 values plugged in. I'm going to plug in a number for A, a number for B, and a number for K. Now in this case, I want to make it easy, so we'll go 2, 3, and 4. Why 2 and 3 and 4? Because I can. I want to choose different numbers, because if I choose the same numbers, there's a chance some wonky mechanics pop out, and like a bunch of stuff randomly cancels. And I'm avoiding 1 because 1 also means the number basically doesn't work. I mean, the A kind of disappears, B kind of disappears. It might be good, but it's not going to tell me the full story. So, let me plug it in. Going to Desmos. And on Desmos, I'm going to look for this equation. Now, as a reminder, the equation I'm going to plug in will be in terms of t. This thing will not graph in terms of t, it will graph x and y values. So when we look at this picture, you cannot be in terms of x and y anymore. The x-axis is the t-axis. The y-axis becomes the position axis. In this problem, that is the other part of physics that makes it more fun and interesting, is you have to remind yourself that this is not algebra. It's not x and y anymore, it's input, output. My input is time, so that means my x-axis is t. My output is the position, so my y-axis is how far away it is. Here we go. My equation. A, so that's going to be 2. Then I have e to the kt, so I'm going to do 3t minus, so that'll be b, so I'm going to make that 4 e to the negative kt. So for this specific function, you can see that it will have, so when t is positive, so that's my numbers to the right, I start off, my position is negative, so at t equals 0, my position is at negative 2. So again, learning to read a physics graph now. When my t is 0, my position is at negative 2. I hit the axes when my position is 0 at 0.116. And I'll bet if we plug in my A, B, and K values, that's the right number we get out. I believe we got ln of B minus ln of A all over 2K. Abby, you have a calculator with you?
Yeah.
Take ln of 4 minus ln of 2 and divide it by 8. And tell me what you get.
What?
ln of 2. No, it would be, so ln of 4, sorry. ln of 4 minus ln of 2 all over 2 times k, which was, oh yes, 6. Divide that by 6. What's the answer?
0.115.
Huh.
Yeah.
Weird.
Crazy.
We found the position is 0. Now keep in mind what the ball is doing according to this formula. So I have to think. Right now, my t value is 0. So at the t value of 0, my ball is at negative 2. At a t-value of 0.16, it's all the way over here at the origin. And then it starts shooting to the right as fast as it can go. Woo! All the way over there. By the time we get to 1 second, like it's way over. That's the physics of this problem. We have to understand that in this picture, my x is not x, it's t. My y is not y, it's the position. So when the position is 0, is at 0.116. When the time is at 0, we are at -2. So the origin is here, the particle is here, moving to the right. Part B of this problem says, show that the acceleration of the particle is proportion to the position. One more time. Part B, we're not going to do it, but part B says, show that the acceleration is proportional to the position. There's two math terms in there we know very well. One of them is more physics. We have the position function. It talks about the acceleration function. What does that mean to do? How many times?
Again, 2 times from the position.
2 times from position. So if we already did it once for your version, we just do it one more time. So doing it their way, we have to do eventually anyways. So it's not a bad way to go. Second, once we have that piece, we then need to show it's proportional. What does the term proportional mean in mathematics?
Same slope, right?
Not the same slope.
They have the same.
They are similar in structure. It means there's a constant multiple separator. Or a good way to check is if you divide this. Okay. We'll talk more physics tomorrow.
Cheyenne Divine.
Looking forward to it.
Cheyenne Divine, please come to the office.
Have a good day.
You too.
Here, pass it.
Sawdust. So much sawdust.
I feel like I need to mention something.
Oh, see you, Devil.
Live.
I feel like you guys are more castle plenty.
Come on, man. It's Monday.
Just
Hey. Could be worse.
I mean, not really. I mean, any other day's closer to Friday or the weekend.
Yeah, but you have to work weekends. So you never have to.
I mean, I normally do work weekends.
See? Then what's the difference?
I mean, school. I don't get paid to do school.
Look at it.
If you think, well, it'd be better than I'd actually enjoy it a little bit more. If you think about it, going to school and through college and then getting a job, it's just really losing so much money. Because think about how many hours you're working but not getting paid to learn, and before you actually start a job. Imagine if you got paid like $10 an hour for all those hours. So it was like, how many days are in a school year?
Days in the school year.
Like school days, yeah.
184 usually.
184 days. So let's do some quick math. 184 days times, let's just say high
Kaden
school is
Land,
4
please come to
years.
the office. Kaden Land, please come to the office.
So that's how many days times 7 hours times $10 an hour. $51,000.
Yep. If you think about it, that's, about how much $10 costs. Yeah.
So what I'm hearing is you'd be better off dropping out before your freshman year, working 7 hours a day, and then getting your GED and going to college.
Maybe.
Fun fact, did you know if we dropped out before freshman year, anyways, if we dropped out before our freshman year started and worked 7 hours a day, only the days we would have been at school, for 4 years of high school, we'd make $51,000. If we made $10 an hour.
What are you talking?
I just had Mr. Dad listen.
You were already talking about before I even got in here.
Well, I'm not So, I was like, you know, school's terrible because you think about all the hours you put in with no money just to get a decent job to make, you know, like decent money. I was like, I wonder how much money you'd make if you just like did go to high school and saved up. And we figured out that you made $10 an hour, only working 7 hours a day for every day we had school, even like not including the days we had like breaks or long breaks, anything. We'd make $51,000, making $10 an hour.
There really isn't that much money.
I mean, that pays, that pays for college.
I know, but for us, like, kid that young, yeah.
For $10 an hour, I mean, it's like 184 days in a year times 4 years times 7 hours a day times 10. But what if it's like what if we made $15 an hour? So that's not like a bunch more. But 77. It's not bad.
You didn't want to think about dropping out now.
That's what I'm saying.
It's a little late.
It kind of makes sense now.
It's a little late, though.
If you're gonna do it, you guys do like your freshman year.
What took so long now to package and stuff? Logan was gone from class forever. Like, a couple hours and
They're probably getting shorts. I got the leave last block, went to like prep, just tasted the chair back in history, and I went to Sticks before I got back.
What is that from? Pretty good.
Pretty good.
Yep, I'm not.
That's gone. I think it tastes like
Well, I taste rose.
Hi, I'm the engineer time.
I don't like it.
Let's murder some
And
each other
it's
again.
16 from your mom yesterday.
Oh my god.
His mom is such. It's his mom. He just. She's so like.
Actually, I'm spring now.
You don't like these?
You wanna put the side needle?
No, egg. No, yeah, hell yeah, these are
There's
good.
a side needle.
That's all I had.
They still had it at 2 o'clock.
So good.
No, they're coming out by like 8.
They just brought some in with that.
And I have one of those about every morning.
I love these. You ever put jelly on? Try grape jelly on.
Dude, I made a sexy picture the other day.
Oh yeah?
You what? I made a sexy picture the other day.
Was it as sexy as Jackson, that one home game I watched, where he dove and caught it? That was a very good catch.
And then that's about it.